Welcome to your last screencast on Chapter 9, where we are going to cover muscle fiber types, energy sources, and aging of muscle. So this will be covered in sections 9.6, 9.7, and 9.10. So we'll begin with the muscle fiber types. There are two main ones I want you to know. We'll start with our fast twitch, which is also known as type 2 muscle fibers. These are going to be the ones that when you want to have explosive power and strength, that you will be using. So it responds rapidly to our nervous system, will also contain myosin that can break down ATP more rapidly than it can in type 1. We need less blood supply, and we have fewer and smaller mitochondria than slow twitch muscle fibers. And we're going to talk about a little bit of a connection when it comes to energy sources for this muscle type. They will also fatigue more quickly, and we will have more of these fibers in the lower limbs in sprinters and in upper limbs of most people. They are going to come in two different types, in an oxidative form and a glycolytic form. Now for our slow twitch muscle fibers, before we move to the slow twitch muscle fibers, the white fibers here are what's known as the fast twitch or type 2 muscle fibers. So think of your rabbit here, how it explosively jumps up. Okay, that's what we think of for fast twitch. Now for our slow twitch muscle fibers, these are also called type 1 muscle fibers. They're going to contract more slowly. We'll also see that they are smaller in diameter when we compare them to the fast twitch. They have a better blood supply and more mitochondria. We know mitochondria is our powerhouse for creating ATP. So we got a lot of ATP here to use for our type 1 muscle fibers. They are also more fatigue resistant when compared to our fast twitch. And we have a large amount of myoglobin. And myoglobin helps to contain the oxygen in order to produce more ATP and utilize this muscle fibers, having more endurance or steady power. You'll see a lot of our postural muscles are going to have these slow twitch muscle fibers, and we'll find more of these fibers in our lower limb than compared to our upper limb. So you want to think of our turtle here, the slow guy. Slow and steady will win the race, right? So these are the marathon runners will typically have more type 1 muscle fibers. So most of our muscles are going to have both slow twitch and fast twitch muscle fibers, but from person to person, you'll see that there will be some variance. So certain people may have more fast twitch muscle fibers and others may have more slow twitch muscle fibers. And through exercise, we can also change the size of our muscle fibers. So we go through a process of hypertrophy that will not increase the number of muscle fibers that we have, but increase the size of the muscle fiber. So this is like the really buff guy at the gym. He's got a lot of hypertrophy going on. We're increasing the myofibrils and increasing the strength due to a better type of coordination of our muscles, especially when it comes to that neuromuscular component of being able to fire that action potential quickly and have the muscle respond to it. We get an increased production of metabolic enzymes, better circulation for those muscles, and also less restriction by fat. We can also have the opposite happen. If you don't use it, you lose it. So this is atrophy that takes place, or a decrease in muscle size. And you can reverse this, except in severe situations where cells die, or maybe you have some type of lesion or severing of a nerve to go and supply that muscle. You need to reestablish that connection in order to get that muscle to hypertrophy again. This is another one of my favorite tables because it really does a great job of comparing your slow twitch and fast twitch muscle fibers. I'm not really going to have you guys differentiate between the type 2A and type 2B. You guys can kind of put these categories together or just focus on the glycolytic rather than this almost intermediate type of fast twitch muscle fiber that has some components that are like slow twitch and fast twitch. So for the sake of our lecture here, I'm just going to compare slow twitch to our fast twitch glycolytic, also known as the type 2B muscle fiber. When we look at the myoglobin content, we're going to see that the slow twitch has a high amount versus fast twitch, which is a low amount. That's because we need myoglobin to contain the oxygen to create more ATP for these slow twitch muscle fibers. Same reason we have many more mitochondria in the slow twitch and many more capillaries, so that we can bring in that fresh oxygenated blood to these muscle fibers. We'll see in the coming slides that this really works and has a high aerobic capacity, whereas our fast twitch muscle fibers is a low aerobic capacity, but has the highest anaerobic capacity. So more on that a little bit later. For fatigue resistance, slow twitch is high. They can keep going and contracting, whereas our fast twitch are going to fatigue very easily. Our myosin ATP activity is going to be slow, whereas in fast twitch it will be high. So we can keep that myosin head attached to the actin filament maybe a little bit longer. Glycogen concentration is going to be low here because we really use a high amount with our fast twitch in order to get the ATP that we need through the anaerobic capacity. We've talked about how our slow twitch muscle fibers will be found in the postural muscles and also in the lower limbs, whereas in our fast twitch, we will find them more in the upper limbs. And so the function of our slow twitch will be maintaining our posture and doing things more that require endurance, such as running a marathon, whereas fast twitch muscle fibers, they are going to be used for rapid and intense movements of short duration, such as doing power clean or something. When we exercise, we are also going to be able to produce heat, and that's because of the metabolic rate and the contraction of our muscles are going to produce the heat. After we finish exercising, our metabolic rate stays high because of oxygen debt, which we'll talk about in just a little bit. And our excess heat is going to be lost because of vasodilation and sweating. So vasodilation, remember, we can bring blood closer to the surface of our skin and have it evaporate off of our skin and into our environment. Also, if we are cold, we can shiver, where we have an uncoordinated contraction of our muscle fibers, resulting in shaking and heat production. Now let's get into our energy sources for muscle contraction. ATP is going to provide immediate energy for muscle contractions, and we could do this through 4 different processes. First is going to be through conversion of 2 ADP molecules into 1 ATP molecule and an AMP molecule through the enzyme adenylate kinase. Our second process is going to be through the transfer of phosphate from creatine kinase to ADP to form ATP. Our third way is through an anaerobic respiration, where we take glucose, put it through glycolysis, and get our ATP in that way. And aerobic is where we take our glucose and put it into aerobic respiration in our mitochondria and get about 36 ATP per glucose molecule. So let's go through each of those one by one. We have our 2 ADP molecules, and what we do is take phosphates. So let's review real quick. ADP stands for adenosine diphosphate, di meaning 2. So we've got 2 phosphates here and 2 phosphates here. And in order to get our ATP, 3 phosphates for adenosine triphosphate, we take one of the phosphates from the ADP through using the enzyme adenylate kinase and give it to the other ADP molecule to get ATP. Now, because we took one of the phosphates from this ADP, that turns into AMP, adenosine mono, meaning one phosphate. And this just produces a few seconds of ATP use for our muscle. Now let's talk about creatine phosphate. So during our resting conditions, we can store energy in the form of creatine phosphate so that we can synthesize ATP. Creatine phosphate is a unique molecule. It's located in our muscle fibers, and we can donate a phosphate to ADP in order to instantly form ATP. So this CP represents the creatine phosphate. Here's our ADP. And in the presence of creatine kinase, our enzyme, we are going to be able to transfer the phosphate over to the ADP molecule and get ATP. We have left over just creatine without its phosphate. And by doing this, we have enough ATP and CP reserves to power a cell for about 15 seconds. Now for our third process, anaerobic respiration, this will take place in the absence of oxygen and will result in breaking down glucose to yield ATP, about 2 of them per glucose molecule, and lactic acid, which will be released into the blood. We will also see intermediately we'll have 2 pyruvic acid molecules form. When we have our lactic acid diffuse into our bloodstream, we can use it as fuel by our liver, our kidneys, and the heart, or it could be converted back into the pyruvic acid by the liver. And our last process is through aerobic respiration. This is always going to require oxygen, so we take glucose from breaking down our glycogen, or it could be delivered straight from our blood. That gets turned into a pyruvic acid, which then goes into the full aerobic respiration process in the mitochondria. Now, we're not going to go through the full cycle of everything in the mitochondria. That is more for a biology course that you've taken. But what we need to know is that we will pump out 32 to 36 ATP per glucose molecule. And we'll also get some other components such as water, carbon dioxide throughout the process. And we can even use fatty acids or amino acids to go through this aerobic respiration process. And if we've been working out for about 30 minutes, then we are going to use fatty acids as our main fuel for this aerobic respiration process. This doesn't have the 4 processes in making ATP in skeletal muscle, but I still really like this table. It contains the 3 different processes and really compares them. So I left this in for you to take a little look through it. Now let's talk about muscle fatigue and soreness. We have a decreased capacity to work and reduced efficiency of performance when fatigue sets in. So this could be caused by acidosis, where we have glucose break down into lactate and protons, which lowers our pH, and also through ATP depletion. So we either have increased ATP consumption from maybe working out too hard, or a decreased amount of ATP production. Maybe we're not getting enough oxygen, or we're not getting enough glucose in our body, or our glycogen has been depleted and we can't get that glucose in order to make ATP. It can also form from oxidative stress, where we have an increase in reactive oxygen species and free radicals causing breakdown of proteins, lipids, and nucleic acids. And third, through local inflammatory reactions. So maybe your immune cells are traveling to damaged muscle and signaling pain to halt further damage. We've also got different types of fatigue. So psychological, which is going to depend on your emotional state, and a lot of the central nervous system is involved there, or physiological type of fatigue, which is what we just talked about, the ATP depletion, oxidative stress, or inflammation. And to kind of go further into that, there's these subcategories of muscular that would refer to the ATP depletion, and the synaptic that occurs when the neuromuscular junction is affected due to a lack of acetylcholine. You may have heard of physiological contracture and rigor mortis. Physiological contracture is a state of fatigue where we have a lack of ATP and we are in a state of neither contraction nor relaxation. So these are the different grades of contracture. You could see that fourth finger here over in grade 3, where there has been a tightening of the connective tissues, including the muscle. We also have rigor mortis that can take place, and this is a development of rigid muscles after several hours after death. So what happens is the calcium leaks into your sarcoplasm and attaches to the troponin, which shifts the tropomyosin out of the way, and those myosin heads attach to actin to form those cross bridges. So that contraction is held in place, and we need that ATP in order to release the myosin heads. But because there's no energy coming, because death has resulted, those myosin heads are stuck there, and the rigor ends as tissues start to deteriorate. Now, after you've been exercising for a bit of time, you might have some oxygen deficit. And this is a lag time between when a person begins to exercise and when he or she starts to breathe more heavily. So after an extended amount of time, you get that huffing and puffing that takes place. We also have excess post-exercise oxygen consumption. And that's going to be the lag time before breathing returns to normal once you've stopped exercising. So this deficit has to be repaid. So when your body is resting after exercise, that's when your body can make up for that deficit. And there are certain metabolic processes that are going to restore your homeostasis. So your body temperature, ion concentrations, metabolite, and hormone levels. So I want you guys to go ahead and skip over 9.8, which covers smooth muscle. We talked about in our digestive system and cardiovascular system lectures, and also skip 9.9, which covers cardiac muscle, which was covered in our cardiovascular lecture. So that brings us to 9.10, which discusses the effects of aging on skeletal muscle. We'll see as we age that we will have reduced muscle mass, and this is called sarcopenia, where our muscle is going to atrophy. We'll also see that that neuromuscular connection isn't quite as strong as it once was, so we'll have increased time for the muscle to contract in response to a nervous stimuli. We'll see reduced stamina. It'll take a longer amount of time to recover after you work out. You'll have a loss of muscle fibers at times and decreased density of capillaries in your muscles. So you're not getting as great blood supply over to those muscles. So that is it for chapter 9. If you have any questions, please feel free to reach out. And just to let you know, I put this table in at the end for you to scan through just to get a little idea of some of the conditions that could take place in relation to the muscular system, but you guys will cover this in a pathophysiology course.